Hi ladies, this is lesson 5.7 and it's applying the fundamental theorem of algebra, which we'll define in just a second. So the first term that you have on your note sheets, is repeated solution. So this is for a polynomial equation f of x that equals 0. There is a repeated solution if and only if a factor of that function has an exponent that's greater than 1. And it's going to be a repeated solution if that function is factored completely and you still have an exponent that's greater than 1. So for example, if you look at this polynomial function, x cubed minus 5x squared minus 8x plus 48, if you factor that completely, and you can factor it on your own if you'd like, but the factors are x plus 3 and x minus 4 squared. Now, if you think of your solutions here, your solutions are, or your zeros, are -3 and 4. Now, since -4 is x minus 4 is squared, you can count 4 as a solution twice. And this is important because of the fundamental theorem of algebra that we'll define in just a second, but because x minus 4 is squared, you have factors x plus 3, x minus 4, and x minus 4. So you have 3 solutions, but 2 of them are the same, which is a repeated solution. So then, looking at the fundamental theorem of algebra, if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. And then the theorem that we're going to look at is if f of x is a polynomial of degree n where n is greater than 0, then the equation f of x equals 0 has exactly n solutions. So the other one was at least one solution, but this talks about exactly how many solutions they have, provided that each solution repeated twice is counted as 2 solutions. So any repeated solution, like in our last example, x minus 4 squared, 4 is a repeated solution. So we have to count it twice. So in our last example again, the degree of this polynomial was 3, so we had 3 solutions. -3, 4, and 4. So if you look at this next example, applying those fundamental theorems of algebra, because x cubed minus 3x squared plus 9x minus 27 equals 0 is a 3rd degree polynomial, or cubic polynomial equation, it has 3 solutions. And the next one, because f of x equals x to the 4th plus 6x cubed minus 32x, because that is a 4th degree polynomial function, or a quartic function, it has 4 zeros. So let's look at this example. How many zeros are in this function? Well, first you should look at the degree. And the degree of this function is 3. So there are 3 solutions. All right, now this next key concept, the complex conjugates theorem. So we've worked with complex conjugates before, remember? A plus bi, and then we multiplied our fractions by the complex conjugate, which is the opposite. So if f is a polynomial function with real coefficients, and a plus bi is an imaginary 0 of the function, then a plus a minus bi is also a 0. So you would have if you think of how you find your zeros, if you factored, your factors would be x minus a plus bi, and you would have another factor of x minus a minus bi. So those would be your factors. If a plus bi is a 0, then a minus bi is also a 0. Now let's look at this next one, irrational conjugates. So if you have a polynomial function with polynomial coefficients a and b are rational numbers, but the square root of b is irrational, if a plus the square root of b is a 0, then a minus the square root of b is also a 0. So what would your factors look like? One would be x minus a plus the square root of b, and another factor would be x minus a minus the square root of b. So now that you know how many zeros you have and what kinds of zeros you might have in a polynomial function, you might have some that are positive, some that are imaginary, some that are repeated, some that are irrational. But actually finding the zeros is a little trickier. You have to know how many you have to start with, so you know how many you're looking for. So let's look at this function. How many zeros am I going to have? Well, my degree is 5. So I know I'm going to have at least 5 zeros. Well, I'm going to have exactly 5 zeros. Now, some of them might be repeating, some of them might be irrational, but there are going to be 5 of them. So in order to find these zeros, I'm going to use synthetic division. I'm going to factor this polynomial function. So let's look at my possible zeros. And that's going to be my p over q. So my factors of -4 and my factors of 1. So my factors of -4 are plus or minus 1, plus or minus 2, or plus or minus 4. All right, those are my possible zeros. That's where I'm going to start. You could also graph to see what your zeros might look like. So I'm going to start by factoring -1. So is x plus 1 a factor? That's my first, that's what I'm going to test first. So is -1 a 0? Or is x plus 1 a factor? Well, let's use synthetic division. So set up your synthetic division with all your coefficients, 1, 0, -4. Don't forget your zeros if you're missing a degree. And I'm going to test -1. And I had actually one of my coefficients from here. This should have been a 1. I had a 2 there. So that's why that 5 should be a 4. And that should be -4. All right, so I get a remainder of 0. That means yes. -1 is a 0. So you're going to have to continue this process until you get down to just a quadratic expression or until you get to a factorable expression, either by grouping or by putting into quadratic form. So I'm just going to rewrite what I have so far. X plus 1 times x to the 4th minus x cubed minus 3x squared plus 4x minus 4. All right, so here's my new function. So now let's look at my potential zeros. So I have 1 0, I'm looking for 4 more. So my zeros, which are my p over q again, are positive -1, positive -2, or positive and -4. All right, now you can look at a graph if you want to kind of give you an idea of where this starts. So I'm going to test 2. So is 2 0? Is x minus 2 a factor? So I'm going to, again, using synthetic division. And I have a 0 remainder, so yes, x minus 2 is a factor. Oops. So I'm going to go ahead and rewrite what I have so far. X plus 1 times x minus 2, x cubed plus x squared minus x plus 2. So again, I'm going to look for my possible zeros. And here I'm looking for, since my leading coefficient is 1, I'm looking for factors of 2. So again, that's p over q, which in this case is just my p's. So plus or minus 1, plus or minus 2. So I've narrowed it down quite a bit. So let's look at -2. So I'm going to set this up like I would normally, synthetic division. And since I have a 0 remainder, then -2 is a 0. All right, now I can again rewrite what I have. All right, now I finally narrowed it down to a quadratic. I've got x squared minus x plus 1. All of that equals 0. So I don't see any factors of 1 that add up to negative 1. So I'm going to use the quadratic formula. And when I do that, I get 2 solutions, 2 imaginary solutions. 1 plus I times the square root of 3 over 2, or 1 minus I times the square root of 3 over 2. So if I look at all of my zeros, I have to have 5. I'll start with my quadratic ones. 1 plus I times the square root of 3 over 2. 1 minus I times the square root of 3 over 2. -1, 2, and -2. Those are all of my zeros. So the next part of your note sheet is trying it on your own. So find all of the zeros. First identify how many zeros you're going to have, and then actually find what they are. And actually this is different than what's on your note sheet, so we're going to do the one that you have on your note sheet so you can follow along. So please pause while you work, and you can unpause for the solution. So your first step is to identify what degree your function is, and in this case it's 3, so you know you're going to have 3 solutions. So now let's actually find what those solutions are. So So listing your possible solutions, positive, -1, positive, -3, positive, -9. I tested -3, and I got a remainder of 0, which means that -3 is a 0, or x plus 3 is a factor. So if I rewrite my function, x plus 3 is a factor, then what's left is x squared plus 4x plus 3. I can factor this. I don't even have to use the quadratic formula. It's factorable with integers. And your factors are x plus 1 and x plus 3. Its factors of 3 are 3 and 1, and those add up to 4. So I have 3 zeros, and in this case, they're all real numbers, but one of them is a repeated solution. So x plus 3, x plus 3. So that's x plus 3 squared times x plus 1. So since x plus 3 is squared, it's a repeated solution, I have to count that -3 as a solution twice. So my solutions, because I have to have 3 of them because it's a third degree polynomial, I have -3, -3, and -1. All right, in this next problem, you are looking for all the zeros in order to write the polynomial of least degree that has rational coefficients, that has a leading coefficient of 1, and 4 and 1 plus the square root of 6 are 0. Actually, I think I skipped a slide, so let's go back. One example. Same idea, though. We're writing a polynomial function of least degree. It has real leading coefficients of 1 and -2 and 3 plus I as 0. So what this means is our factors, if -2 is a 0, we have a factor of x plus 2. If 3 plus I is a 0, we have a factor of x minus 3 plus I. And if 3 plus I is a 0, then 3 minus I is also a 0. So we have another factor of x minus 3 minus I. Now, in order to write our polynomial function, all we're doing is multiplying this out. So we're going to use the distributive property, add our like terms, and then use the distributive property again, and add our like terms again. So first I'm going to use the distributive property with the negative sign. And then I'm going to multiply my two trinomials for my binomials with complex numbers. So x times x is x squared minus 3x plus xi minus 3x plus 9 minus 3i minus xi plus 3i minus I squared. Right, I'm going to add my like terms together. Got x squared minus 3x minus 3x is minus 6x. And then plus xi minus xi, that cancels out. Minus 3i plus 3i, that cancels out. And I have plus 9 and minus a negative 1, because I squared is negative 1. So that's plus 1. All right, so I'm going to add my like terms. And then lastly, distribute. X cubed minus 6x squared plus 10x plus 2x squared minus 12x plus 20. And now, again, lastly, add my like terms. Minus 6 plus 2 is minus 4x squared. Plus 10 minus 12 is minus 2x plus 20. So I have 3 zeros, and so my leading coefficient they gave us was 1. And since I have 3 zeros, my degree of this polynomial function is 3. All right, try the second one on your own. First, identify the zeros, then identify the factors, and then find the polynomial function by using the distributive property. Please pause while you work, and you can unpause for the solution. So first step, identify your zeros. You have 3 zeros, so you're looking for a polynomial function that has a degree of 3. Identify your factors and write it in factored form. Now just use the distributive property to find your polynomial function. So your final answer, and check all your steps if you have something different, but it should be x cubed minus 6x squared minus 27 plus 140. That's your polynomial function, degree of 3, leading coefficient of 1. All right, this next concept is Descartes' rule of signs. So this says that the number of positive real zeros is equal to the number of changes in sign of the coefficients, or less than this by an even number. So it could be 3, or it could be 1, or it could be 2, or it could be 0. So the number of negative real zeros is equal to the number of changes in sign of the coefficients of f of negative x, or less than this by an even number. So again, it could be 6, or 4, or 2, or 0, or 5, or 3, or 1. So it's going to go down by even numbers. So in this next example, determine the possible number of real positive real zeros. So changes in sign of f of x. Negative real zeros, changes in sign of f of negative x. And imaginary zeros. The imaginary zeros are whatever is left over. All right, so we're going to look at first the function f of x and the changes of signs. So this is positive to negative. That's one change. Back to positive. That's 2 changes. That means that there's 2 positive real zeros or 0 positive real zeros. Now let's look at f of negative x. F of negative x, if this x to the 5th power was a negative x, you would have negative 2x to the 5th. So your odd degree coefficients are going to change, but your even ones are going to stay the same. So that would be minus 12x cubed plus 2x squared minus 4x plus 6. So let's look at your changes. So still negative, 1, 2, and back to positive. So that's 3. So there's 3 changes. So since there's 3 changes, there could be 3 negative real zeros or 1 negative real zero. So for your imaginary solutions, if there are 0 positive real zeros and 1 negative real zero, that means there could be 4 imaginary. If there's 1 negative zero and 2 positive, that means there could be 2 imaginary. There has to be 5 total. And if there's 0 positive and 3 negative, there could be 2 imaginary. Or if there's 2 positive and 3 negative, then there would be 0 imaginary solutions. Right, so in this next one, try this one on your own. You can pause the video while you work. But you're using Descartes' rule of signs to determine real positive zeros, negative real zeros, and imaginary zeros. And you can unpause for the solution. Right, so first you're finding the changes in f of x, which is 3. So your positive real zeros could be 3 or 1. Then you want to substitute in negative x for x, and you'll find that the changes of f of negative x are 2. So your negative real zeros are 2 or 0. And then lastly, find how many imaginary solutions you have, because you need 5 total. So if there are 0 negative and 1 positive, you could have 4 imaginary. Or if there are 0 negative and 3 positive, you can have 2 imaginary. Or if there are 2 negative and 1 positive, you can have 2 imaginary. Or if there are 2 negative and 3 positive, you can have 0 imaginary. So please jot down any questions that you have in this lesson, and go back and watch and rewind and replay parts of the video as needed, and come in with your questions and you can go over them next time I see you in class. Thanks.